In the previous lectures, we had seen how stability had to do everything with the location of poles. For a second order system, I can use my high school algebra to compute the location of the poles. Systems of the order of 3, s cube, and so on, I can still have some methods analytically to solve them. What happens if I have polynomials of higher order? Say my system has 6 poles or 8 poles or even 10 poles. How do I check for stability? In the modern context, I can use powerful computational tools in the form of MATLAB or any other softwares that are available to solve these equations. But how did these things come into being? How would people check for stability before powerful computers were invented? So that brings us to the technique called the Routh Hurwitz criterion. Towards the end of the lecture, we'll also look at a bit of the historical context of this, of how everything related to poles came into being, how the theory evolved, how was the first stability theory devised, and so on. So a general transfer function will have a polynomial in the numerator and a polynomial in the denominator. And QS, so this is the characteristic equation of order n. The system will have n poles, which will come via solving these characteristic equations. For stability, it is necessary to determine whether any of the roots lie in the right half plane, right half of the S plane. And the characteristic equation can therefore now be factored as a set of poles, right? So all this multiplication of S minus P1 till S minus Pn. Let me do a quick recap from what we know. So if I write down what is, say I have S minus P1, S minus P2. This is, I can write this S square minus P1 plus P2 S plus P1 P2. Now to this, I add, I'm looking at now what is S minus P1, S minus P2, S minus P3. So this is S square minus P1 plus P2S plus P1 P2, and I have a S minus P3. So S cube minus P1 plus P2 S square plus P1 P2 times S. Then I will have terms which will be corresponding to P3. I'll have a minus of P3 S square. Then I will have a plus P3 P1 P2S, and towards the end minus P1 P2 P3. So this is S cube minus P1 plus P2 plus P3 S square plus P1 P2 P1 P3 P2 P3 times S minus P1 P2 and P3. Okay, look at this thing, right? So if I have my roots factored in this form, what sits in the coefficient of S square is the sum of all p's. What sits here is multiplication of two of those at any given time, and at the end is the multiplication of all of this corresponding to S power 0. Now I can generalize this to say the following, right? So multiplying all the factors, I have Q of S is, okay, so the AN here is 1 in our case, what we are seeing. S power n minus 1 will have the sum of all the p's. This is the sum. S power n minus 2 will have two components multiplied at each time. That is Pi, Pj, and all the way until I end up with the product of all the poles with negative 1 power n. Okay, to ensure that the roots of the characteristic equation lie in the left half of the S plane, it is necessary, therefore, that all the coefficients are non-negative, and all the coefficients have the same sign. Okay, now this is a general rule for a necessary condition for the roots of the polynomial to be in the left half plane. Okay, so why do we say this, that all the coefficients must be positive or of the same sign? So I'm interested in the signs of the pi and so on. So this all these pi's, if I write it in the form of s minus pi, my pi must be should be less than zero for the system to be stable. Okay, so I look at all these things. So an minus 1 over an is the summation of pi. An minus 2 over an will have all the products of two roots and so on until we reach an. So for all these pi's to be negative such that the poles are on the left half plane, the ratios all should be non-negative and or of the same sign for the system to be stable. Of course, is this condition enough? Well, these are only necessary conditions. So these are only necessary conditions, but not sufficient. What does that mean? So look at this polynomial here, s cube, s squared, 2s, and 8. All the coefficients are positive, but I see that the roots are, okay, this is stable, but these two are unstable, which means all the coefficients are positive or all the coefficients are negative doesn't ensure always that the system is stable. It's only a necessary condition and not a sufficient condition. So we go to the Routh Hurwitz criterion, which is both a necessary and sufficient condition for the stability again of LTI systems, because we can write it in a nice transfer function form. The method is a two-step process. First is generating what we call a Routh array and interpreting the Routh array for locations of poles in the list. So the criterion states, as we will see with the help of the procedure, that the number of roots of the characteristic equation with positive real parts. So if I say there are no roots with positive real parts, which means the system is stable, right? So it states that the number of roots of the characteristic equation with positive real parts is equal to the number of changes in sign of the first column of the Routh array. Okay, it's too much of text, but let's try to understand this. So I construct a table. It's a bit of a step-by-step process. I construct a table. So this is my given polynomial. I start with s power n. I write all the alternate coefficients. I have an minus 2, an minus 4. I go to Sn minus 1. Here I write again all the alternate coefficient, an minus 1, an minus 3, an minus 5, and so on. And the remaining rows are formed by computing each of these bn minus 1, bn minus 2, cn minus 1, cn minus 2, and so on. Okay, how are these computed? So bn minus 1 is, sorry, bn minus 1 starts by computing an minus 1, an minus 2 minus an minus 3 divided by the term just above it. Okay, similarly, I can also look at computing what is bn minus 2. Okay, so once we have computed bn minus 1, I can compute cn minus 1 again by looking at the same formula. So now it's like I'm looking at the negative determinant of the matrix which just sits above and divided by the coefficient just above what we are computing. So similarly for cn minus 2 and so on. Okay, so it's a bit of a mechanical process, but we will see what does this mean. For a system to be stable, we had read out this long statement here, rating stability. So this means the following, that I compute all this an until I reach the coefficient of s power 0. And I go from an to an minus 1. I ask myself if there is a sign change. As long as there is no sign change from an minus 1, an minus 1, bn minus 1, so far, if all of these are of the same sign, which means there is no sign change, then the system is stable. Okay. If there is a sign change, which means the system is unstable. How is it unstable? Because each sign change corresponds to a root in the right half plane. So number of sign changes is equal to the number of roots in the right half plane. Okay, now I just do a quick illustration. I have a third order system, s cube, 4s square, 9 and s. I construct my Routh table. I start with s cube. I go with the coefficients of the alternate terms. I have a 1, I have a 9, then the 4 and the 10 come here. I compute this by using the formula stated in the previous slide. Okay, I'll try not to memorize it, but it's a straightforward thing. Then I compute the coefficient of S0. I go 1, 4, 26, 4 by 4, and 10. What I see is that all the elements in the first column are positive, and hence the system is stable. Okay, so I can, if we have, okay, quickly we can look at this one, 1, 1, 2, and 8. I had S cube plus S square plus 2s plus 8 was equal to 0. If I just draw the Routh table for this, I have Sn, which is a 1, a 2. I have this will be S cube, S square will be a 1 and a 8. So I'm looking at what happens to S power 1. Uh, so I'm looking at computing this will be uh, uh, this will be 8 minus 2 by 1. So this will be 6 here. Now I compute s power 0. No, this is, okay, let me see. What's the order of the computing? It is an minus 1 into an minus 2. I take the determinant and the negative of that. So determinant of 1, 2, 1, 8. So this will be 8 minus 2 is 6. And what I should show up here is a negative of this. And you see there's already a sign change. Okay, and therefore I see one sign change. I just stop here. I say that the system is unstable. Okay, then you can compute the next step also. When I have 1, 8, negative of 6, and 0. The determinant of this is, so this should be a plus 8 here. And this, you see that two sign changes, which means two poles in the right half plane. Okay, so that is what we see in this, right? So I have two poles here in the right half plane. Okay, this kind of gives me a little idea of how to interpret the right Routh table in terms of stability. If there is no sign change, the system is stable. There are two sign changes, as in this case, the system is unstable with two poles on the right half plane. Okay, now these things are not always easy. Now let me take this fifth order polynomial. So I write the Routh table, start with s power 5. I have 1, I have 2, I have 3. Then I have 1, 2, and 15. I do the little computations. It turns out that I get a 0 here. If this is 0, this coefficient is undefined because I divide something by 0. Okay, so what is happening here is that the first element is 0, and whenever the 0 we encounter a 0, we just replace it with a small number epsilon. Okay, and the epsilon is such that the so small that it's if it's allowed to approach 0, the sign is interpreted appropriately for stability. I'm just looking at a very small what happens to the Routh table when there is 0. I replace it with a small positive number, say epsilon, and the value of epsilon is allowed to approach 0, and we see what is the sign of the entries, and we can interpret it based on these signs as epsilon goes to 0 and the stability things remain the same. Okay, so now I replace this number with an epsilon, and then now I compute the table as if I'm looking at 1, 2, epsilon, and 12. So 1, 2, epsilon, and 12. So this will lead to me a number like this here, here, and here, right? So what happens when epsilon tends to 0? When epsilon tends to 0, this is positive. When epsilon tends to 0, this becomes negative, and this becomes positive. So we see two sign changes. Yes, as listed here. So no sign change, one sign change, another one sign change. Okay. So the system therefore is unstable because we see two sign changes in the first column of the Routh array. Okay, more cases. So I look at this particular equation, s cube 5s square 6s and 30. So okay, so I try constructing the table. I write my coefficients for s cube, which is 1 and 6. S square is 5 and 30. S power 1 becomes 0 and 0. Okay, now if an entire row is 0, what do? We knew what to do when there was just 0, there's one element is 0, replace with epsilon and calculate everything as limit epsilon actually goes to 0. So if an entire row is 0, an auxiliary polynomial is formed with the entries of the row immediately above this. Okay, so this auxiliary polynomial is differentiated now with respect to S, and after we differentiate, we get entries for this row. Okay, and now we interpret the roots. Okay, let's actually learn what we are doing now. So I have a 0 and a 0 in the S power 1. So I just look at what is just above. Just above is a polynomial in S square. So I have 5S square plus 30 equal to 0. I differentiate this with S. So this is equal to 10S plus 0. So I write a number 10 here, and then I compute the remaining entries. So this is 1, 5, 10, and 30. No sign change. System is stable because all the elements in the first column are positive. There is no sign change. Hence, the system is stable. Not only that, if I just solve for this 5s square plus 30 equal to 0 will give me s square plus 6 equal to 0, or s equal to plus minus j root of 6. Okay, now of course, because of these roots, the system is not asymptotically stable, but it's only marginally stable. Okay, so whenever there is an entire row going to 0, this means this exposes a possibility of imaginary roots. Okay, how do I find which are the imaginary roots? Well, I just solve for the auxiliary equation just above this. Okay, this is nice. Is that all? Okay, so what is this special case now? If the auxiliary equation is an even polynomial, so here it was an even polynomial, right? I had 5s squared plus 30. And I concluded that the roots are imaginary and therefore the system is only marginally stable. Okay, if this is an even polynomial, s squared, s4, and so on, in which the exponents of s are even integers or 0, then the roots are symmetric about the origin. The symmetry occurs under condition that of course the roots are symmetric and real. Roots are so this becomes symmetric and imaginary, and the roots are quadrantal about the two axes of the S plane. So these are the possibilities. If there is a j omega, there is a negative of j omega. There is this, there is this, if there is this, there is this, and also if there is this, there is this, and so on. Okay. So we will see now what happens when I have an odd polynomial. Polynomial of degree 5. I have s power 5. Coefficients would be 1, 2, and 1. And s power 4, I have 2, 4, and 2. You see that this row is just a twice of this one, right? So this row 2 is just a twice of row 1, and therefore I get zeros here. So the entire row for S3 is now 0. I now have an auxiliary equation which looks like this. And I solve for, and I do the differentiation. Then I replace this with a 4 and a 4. I can divide the entire row by 4 to get a row corresponding to S3 as 1, 1. Again, I just do the computations. I get 1, 1 here. But then again, I get an equation which now says that the row corresponding to S1 is 0 and I'm looking at a polynomial s squared plus 1 equal to 0, or roots at the form s equal to plus minus j omega. Now I look at, because this also will give me the roots of the equation, right? So overall, it turns out that, of course, there is no sign change in the first column. The roots of the image of the auxiliary equation. So this is the first auxiliary, the second auxiliary equation. This is the first auxiliary equation. The roots turn out to be plus repeated roots at, I have roots at plus j, minus j, also again at plus j and minus j. And what we know is that whenever there are repeated roots on the imaginary axis, the system is unstable. On the other hand, if I have j2 minus j2, j1 minus j1, this system is marginally stable. But if they are repeating at the same at the same instance, that if you have root at plus j minus j, you have another root at plus j minus j, then the system is unstable. We did this lot of this analysis while we learned the topics on stability. So these are how people traditionally used to compute or infer stability for higher order polynomials, much before high power computing equipment came into place. What is the history of this? So we go back to the 19th century when J.C. Maxwell and others became interested in stability of dynamical systems. So Maxwell was essentially interested in the theoretical analysis of centrifugal governors. Well, one of these days we'll talk a little more on detail of this when we talk of controllers. So this was invented in 1788 by James Watt for the precise control of his steam engine in the in the presence of variable loads and variable fuel supply conditions. So Maxwell was the first to give a theoretical analysis. He could not solve the problem, but he came up with some conjecture. And his conjecture was that, listen to this carefully, that the condition for stability of the plant, which in case was the governor, is mathematically equivalent to the condition that all the possible roots and the possible parts of the impossible roots. Okay, possible roots. There was no former notion maybe of complex number those days. Possible roots for all these real numbers. Okay, so this could be 2, minus 2, and so on. And then he talked about the possible parts of the impossible roots. Say minus 2 plus j2 was an impossible root, but then there was a possible part, which we now know as the real part. Okay, possible parts of the impossible root have a certain equation that shall be negative. This corresponds to negative poles. He says he was not able to completely determine these conditions of higher order, but he thinks that this might lead to somewhere for mathematicians. Okay, so he posed this problem at some point of time. It took about 7 or 8 or 9 years for somebody to prove stability. And it's when these two people called Edward Routh and Routh Hurwitz came up with this independently to the result of what is now famously known as the Routh Hurwitz stability criterion. Okay, that's the interesting part of the story. We now learned a little bit of analytical techniques to verify stability for higher order systems, namely the Routh Hurwitz criteria. Sometimes it fails, but we know how to get around those cases with special cases. In the upcoming lecture, we will look at not analytical techniques, but some more graphical techniques. Again, these were things when computers were not freely available or not powerful enough. How did people solve problems in those pre-computer eras? And this will also give us a lot of insights into design. So that will be called as a root locus techniques. That is coming up in the next lecture. Stay tuned for that. Thanks for listening.